Okay, let's jump right into this explainer and completely demystify one of the absolute most notoriously challenging, mark-draining areas in all of Cambridge physics. We're talking about calculating energy released using the legendary equation E equals c squared delta m. Now, whether you are studying for the core 9702 A-level syllabus or building your foundations in 0625, 0651, 0652, or 5054, you already know that nuclear physics can honestly feel a bit like learning to play complex jazz music. You see the sheer beauty of the physics, and you might just want to jump right in and improvise on the exam page. But here's the reality. To be a true master, you have to know the foundational rules intimately before you can even think about operating creatively. Today, we are going to look at the exact, uncompromising rules that Cambridge examiners use to grade your papers. The principal examiner reports state very clearly, and quite sternly I might add, that calculating energy released using E equals c squared delta m is consistently one of the most misunderstood areas in the entire physics syllabus. It's a place where top students suddenly stumble. But we are going to fix that right now. We're going to transform how you approach these multi-stage calculations, moving you from a place of hesitation and confusion to absolute clinical precision. We are going to build a system so robust that you'll actually look forward to seeing these questions on your paper. So here is our roadmap for today's session. First, we'll outline the nuclear physics challenge. Then we'll dive into top examiner warnings. After that, we'll explore the theoretical architecture. Next, we'll break down the method mark strategy. And finally, we'll master the deconstruct, solve, evaluate framework. Let's kick things off with Section 1, the nuclear physics challenge. To really understand this challenge, I want you to imagine two typical hardworking candidates taking the 9702 exam. Let's call them Alex and Sam. Now, Alex is the kind of student who knows literally every single physics fact in the textbook. Alex's brain is a supercomputer of raw data. But when Alex sees a 5-mark nuclear physics question, they completely overload their answer with all that raw data, brain dumping everything they know about protons and neutrons, but providing absolutely zero structural analysis. There's no flow. On the other hand, we have Sam. Sam is sharp, but Sam rushes through the paper. Sam panics at the very sight of a complex multi-stage calculation, entirely misses the specific command word requirements, like the difference between state, calculate, and determine, and just starts frantically crunching numbers. According to the senior examiners, candidates exactly like Alex and Sam are the primary reason why this specific topic sees such a massive, heartbreaking drop-off in scores. It is almost never about a lack of raw knowledge. It is a fundamental lack of strategy. We really have to ask ourselves here, why do so many highly capable students find multi-stage analysis and method marks in nuclear physics so incredibly hard to secure? Think about it. When you are given a question involving mass defect and binding energy, you aren't just plugging random numbers into a calculator and hoping for the best. You are being asked to navigate a highly specific multi-stage problem. First, you have to meticulously find the change in mass, the delta M. Then, you have to ensure your units are perfectly aligned. Are you in atomic mass units or kilograms? Then, you apply the speed of light squared. And finally, you convert that resulting energy into the specifically requested format, like electron volts, or mega electron volts, or joules. Students hemorrhage marks because they treat a complex 5-mark question like a simple 1-mark recall question. They skip vital steps. They refuse to write down their working. They attempt to juggle the entire complex mathematical calculation in their heads, and the very second a tiny, microscopic decimal error happens, the whole answer completely collapses and they lose everything. That brings us right into Section 2, top examiner warnings. Let's look directly at the principal examiner reports to uncover the absolute most common pitfalls. Let me be clear. These aren't guesses. This isn't speculation. This is the hard, unfiltered data straight from the very people who hold the red pen and mark your papers. They have identified specific, recurring errors that candidates make year after year after year when tackling E equals c squared delta m. If you can anticipate these warnings right now, you immediately place yourself in the top tier of candidates. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGSC to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so looking at these mistakes brilliantly illustrates the reality. Students aren't just forgetting the formulas, they are falling into the classic, totally avoidable trap of applying the wrong approach to the wrong context. Let's break down these top 3 mistakes. First, using the wrong approach for the context. This happens when a question asks you about a very specific fission reaction, but you just blindly apply the logic of a fusion reaction because that's what you revised last night. Or you calculate the binding energy per nucleon when the command word explicitly asked for the total energy released. Command word decoding is absolutely critical here. Second, forgetting the check format and presentation. Guys, this is a total tragedy. You do all the heavy lifting, all the hard physics perfectly, but you leave your answer in standard scientific notation when the question specifically demanded a standard decimal format, or you completely butcher your significant figures. Third, providing answers not specific to the given context. If the examiner gives you a specific isotope, say uranium-235, your final analytical answer must relate directly back to the physical reality of that exact isotope, not just some generic, memorized textbook definition of radioactive decay. Now, I want you to really notice the stark contrast here between the vague phrasing students often use and the highly precise, clinical definitions that Cambridge examiners absolutely demand. Think about a time you tried to explain a complex physics concept to a friend in the hallway. You probably used pretty loose language, right? Oh, mass turns into energy, you might say. But in an intense exam setting, that vague terminology is a lethal trap. The theoretical architecture of nuclear physics rests entirely on precise definitions. When you write mass turns into energy, an examiner literally cringes. To secure maximum marks, we need to apply a structured framework. Think of the Peel framework: point, evidence, explanation, link. Your point needs to be razor sharp. What you actually need to say is, the mass defect, delta M, which is the precise difference between the total mass of the separate constituent nucleons and the combined mass of the nucleus, is equivalent to the energy released, calculated by E is equal to c² delta M. Do you see the massive difference there? One is just a casual conversation. The other is a professional, highly analytical statement demonstrating a clear causal relationship. You provide the evidence with your calculation, you explain the physical phenomenon, and you link it back to the command word in the prompt. This specific examiner alert right here is the ultimate warning sign that loose terminology will instantly sabotage your hard-earned score. The examiners explicitly and repeatedly report that candidates consistently confuse key terminology. Listen, you simply cannot mix up mass defect and binding energy. You cannot casually confuse nucleons with nucleus. These aren't just big words, they are the fundamental building blocks of the entire topic. If your terminology is fundamentally flawed, the examiner is forced to assume your conceptual understanding is flawed. And when that happens, the marks slip away in an instant, regardless of whether your final mathematical calculation at the bottom of the page happens to be correct. You have to speak the language of physics flawlessly. Let's move to Section 3, the theoretical architecture. To build a truly unbreakable exam strategy, we must first understand the theoretical architecture of this topic. This is where we stop looking at just the surface-level numbers and start looking at how Cambridge actually constructs the syllabus behind the scenes. If you understand the architecture, you understand the mind of the examiner. Top-performing students, the ones who consistently score A stars, don't view E equals mc² delta M in isolation. They exhibit a deeply connected conceptual understanding that bridges multiple areas of the syllabus. Notice the third bullet point on the screen right now, integrating with other syllabus areas. The principal examiner reports highlight that candidates who reference cross-topic connections achieve significantly higher marks. For example, understanding how the energy released in a nuclear reaction directly relates to the kinetic energy of the resulting particles or the conservation of momentum, or even electric and magnetic fields if you are dealing with the curved trajectory of an alpha particle emitted during that decay. It is all deeply connected. You must demonstrate causal relationships. Why exactly does the mass decrease? Because energy is released to the surroundings. Establishing that solid cause and effect chain is exactly what pushes you into that top grade boundary. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSC to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSC and turn on all notifications so you never miss our weekly exam strategy sessions. Always remember that your exam questions are deliberately and carefully targeting 3 distinct cognitive domains, going way, way beyond basic rote memorization. The examiner is testing your knowledge and understanding. Do you actually know the E equals mc² equation and what the symbols represent? Then they are testing your application. Can you take that equation and use it flawlessly in a totally unfamiliar context, perhaps calculating the energy release for a hypothetical element you've never even seen before? And finally, they are rigorously testing your analysis. Can you look at a complex curving graph of binding energy per nucleon, analyze the subtle trends, and accurately predict which elements will undergo fusion versus which will undergo fission? This 3-part structure is the core framework of every single paper you will ever sit. Moving right along to Section 4, the method mark strategy. Okay, so the absolute most crucial point here is learning exactly how to capture every single available point through the method mark strategy. This is where marks are actually awarded for your process, not just your final answer. Listen to me. This is the absolute game changer. In complex nuclear physics problems, the final numerical answer is often only worth one single mark out of a massive 4 or 5 mark question. The vast bulk of your grade comes directly from your method. If you make a tiny, silly calculator error at the very end, but your written method is flawless, you can still easily secure 80% of the marks for that question. You must develop the muscle memory to follow this exact standardized sequence for the systematic processing of complex energy calculations. Let's treat this like a high-speed interactive workshop right now. Imagine I just put a complex physics data source, a massive table of isotopes and masses on the screen. Let's put 60 seconds on the clock mentally for Challenge 1, Data Scan. Step 1. Identify the key elements. You scan that complex data rapidly. Are they giving you atomic mass units, or are they trying to trick you with kilograms? You have to extract the core trend immediately. Step 2. Apply relevant principles. You physically write down E is equal to mc squared delta m on the page immediately. Don't just hold it in your head. Step 3. Execute analysis with clear working. This means writing down every single substitution. Massive reactants minus massive products. Show it all. Step 4. Verify results. Take a breath. Does the magnitude of this energy actually make physical sense for a nuclear reaction, or did you just calculate an energy smaller than a photon of visible light? Step 5. Present in the appropriate format. This sequence is your ultimate safety net. If you skip from step 1 straight to step 5 by doing it all silently on your calculator, you are completely throwing away your insurance policy for method marks. Presentation is a highly professional skill in physics. Adhering to these strict conventions is absolutely not optional if you want the highest possible grade boundary. Let's do challenge 2 mentally. Find the flaw. Imagine a sample physics paragraph where a student writes a huge block of text but doesn't annotate a single calculation. That's a massive flaw. This is exactly where candidates like our hypothetical rushing student Sam lose marks. When you are doing a multi-stage calculation, you must use proper headings. Actually write the words massive reactants equals and massive products equals on separate lines. Clear annotation of your mathematical working shows the examiner exactly what you were doing. Now for challenge 3, speed writing. If you had 30 seconds to write one perfect PL paragraph explaining your calculation, you'd make sure your point is clear, your mathematical evidence is shown, your explanation of the physics is solid, and you link back to the unit required. If your exam paper is a chaotic, disorganized mess of numbers scribbled sideways in the margins, the examiner literally cannot award you method marks because they simply cannot follow your logic. Use correct and professional terminology and ensure your numerical formats perfectly align with standard scientific conventions. And finally, Section 5. Deconstruct, solve, evaluate. Let's equip you with the ultimate tactical framework, the complete physics answering system to attack any unfamiliar nuclear physics context. The examiners absolutely love to throw curveballs. They will give you an isotope you have literally never heard of, or a bizarre decay chain that looks incredibly complex. When you face this, you do not panic. This is where you apply the 3 rules that guarantee top marks: command word decoding, Peel framework application, and your time management matrix. When tackling long examination questions, you deconstruct the problem, extract the data, and execute using this precise logical sequence. Step 1, identify given information. Extract the relevant data from the intimidating wall of text. Step 2, break the problem down into logical steps. Ask yourself, do I need to find the mass defect first? Yes. Do I need to convert atomic mass units to kilograms using the constant provided in the formula sheet? Yes. Step 3, solve systematically utilizing the strict presentation conventions and the Peel structure we just discussed. Step 4, check for reasonableness. Again, if your calculated energy release is somehow larger than the energy of a dying supernova, you've probably made a conversion error. And finally, Step 5, make justified recommendations or conclusions based firmly on your analytical findings. This blueprint is exactly how you deconstruct the challenge and guarantee those marks. Top-scoring candidates consistently prove their high-level evaluative thinking by actively questioning assumptions and carefully evaluating the quality of their evidence. Sometimes, a particularly tricky question will ask you to critically analyze a given set of data or a specific theoretical nuclear model. You need to confidently identify the limitations of the calculation. For instance, are we assuming that absolutely all the mass defect converts purely into kinetic energy of the fragments, conveniently ignoring other potential energy losses like gamma radiation? Acknowledging the inherent assumptions made and applying the E equals c2Deltam model in a messy real-world context shows a level of maturity and depth in your physics understanding that examiners actively and heavily reward. You must explicitly assess how these limitations might slightly skew or affect your final conclusions. Furthermore, if a question's command word asks for a comparative analysis, you must step up and use comparative connectives to highlight both similarities and differences, backing each single point up with hard mathematical evidence. Often, you will be asked to compare two entirely different nuclear reactions, say the energy released in a heavy uranium fission event versus a light hydrogen fusion event. Let me tell you, it is simply not enough to just vaguely list separate facts about both and hope the examiner figures it out. You must actively identify the similarities and the differences. You need to use strong comparative connectives like whereas, similarly, or in contrast. And, crucially, you must support each comparison with concrete evidence from your calculations, drawing definitive conclusions about their relative importance and efficiency. This is exactly the analytical depth the Cambridge syllabus demands from its top scholars. Let's wrap this up with the golden rule, because the examiner reports are explicitly, unavoidably clear on this. Always define your terms before using them in extended responses. Do not just blindly start writing formulas. Set the stage. Show the examiner you know exactly what mass defect means before you even begin to calculate it. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. I will leave you with this final pivotal question to deeply consider during your next exam. Are you losing critical grade-defining marks simply because you skipped defining your terms before launching into your calculations? Think about it. Good luck and stay strategic.